The big question for this segment is, how can the level of complexity increase? The early universe was very simple. Today's universe is also simple, but today, in very special environments, such as the surface of our Earth, as we've seen, where solids, liquids and gases all seem to mingle, things can get staggeringly complex. How and why? For physicists, the emergence of more complex things is a problem, because they know that the general tendency of the universe is to get simpler. That, by the way, is the second law of thermodynamics, which you'll hear more about later. So, no wonder most of the universe is still pretty simple today. The second law of thermodynamics explains why we should not take complexity for granted. There's something here that needs to be explained whenever we see something more complex appear. One of the great mathematicians of the 20th century, John von Neumann, showed that you could set up a relatively simple pattern of squares on a theoretically infinite chessboard. Each square can exist in one of several states. Then introduce rules for how each square changes depending just on changes in the squares next to it. This, by the way, is known as a cellular automaton. Like the universe, you now have things, you have the ability to change, and you have rules that determine how things change. You have the equivalence of matter, energy, and fundamental laws. Now let the simulation run. Remarkably, von Neumann showed that some of these patterns will become more complex over time. Some will link together to produce larger patterns that can produce even larger patterns. Some will reproduce themselves, and you can even use their evolution as a sort of computer. So, something complex has emerged from something very simple. This was a profound insight into the very nature of the universe. So, we start with things, with energy, and with rules. The things and the rules seem to have been fixed from the moment of the Big Bang. But what about the energy? The first law of thermodynamics tells us that the amount of energy in the universe is fixed. But the second law of thermodynamics tells us that the form and nature of energy is not fixed. Most energy is chaotic, like the random jiggling of atoms in a jug of hot water. It pushes every which way. This is heat energy, and it's the normal form of energy. So eventually all energy will turn into heat energy. Physicists say that randomness, they call it entropy, should be increasing. But sometimes energy takes more structured forms. It seems to flow in a particular direction, like water going over a waterfall. Energy that flows down gradients is known as free energy, and only free energy can do work. So, where energy flows in more organized ways, it can create complex things. But the bad news is that as it flows, energy becomes more chaotic. It turns into heat energy. Eventually, all free energy will turn into heat energy, just as rivers eventually disperse when they reach the sea. And that's why eventually, gazillions of years in the future, all complex things will break down into mush everywhere in the universe. Meanwhile, though, we live in a young universe with lots of flows of free energy. And yes, the electricity that powers your computer is free energy from the physicist's point of view, even though you pay for it, because producing it is not free. The flows of energy in a young universe can generate more complex things. This means that it's interesting to measure the flows of free energy that power complex things. Indeed, they may provide a measure of how complex things are. The astronomer Chaisson argues that you need denser flows of free energy to make more complex things. That is to say, you need more energy every second passing through each gram of matter. Here in graphic form are some of his calculations. Remarkably, they seem to show that the flows of free energy through living organisms are much, much denser than those through a star, such as our sun. And they seem to show that flows of energy in today's world the world of the Anthropocene are much higher again. Chaisson's idea suggests that we should be able to rank things by their levels of complexity, from the simple early universe to the more complex world of stars, to the even more complex world of complex chemicals, to the even more complex world of life, and onwards to the modern global society of the Anthropocene epoch. In this course, as we slowly turn the crystal of complexity, we'll look at many of these different levels. But surely there is more to complexity than this. And of course there is. In the rest of this course, we'll see that complexity is too complex to be captured adequately by such a neat idea. The second module of this course will deal with simple complex systems, or complex physical systems. These are systems like von Neumann's cellular automata, in which the individual components seem to behave according to precise rules. Module 3 will introduce a new level of complexity with complex adaptive systems. These are systems like living organisms, like yourself, in which each of the components is itself complex and behaves in unpredictable ways. Think of the movements of the stock market, or the weather, or the simplest of bacteria, or, frankly, of your best friend. At this point, things begin to get so mysterious that it begins to look as if we're dealing with things that have purpose, with intention. Things such as you and me seem to wriggle. So where did purpose, agency, meaning come from? Frankly, we don't really know. Module 4 deals with human history, which is saturated with agency and intentionality and purpose. Why have we humans become so powerful? We don't yet have a complete understanding of what makes us so different, but we do have some interesting ideas. And we can trace our growing power through more than 100,000 years of human history. Module 5 picks up another theme. If complex things are sustained by flows of free energy, what happens if those flows falter or fail, or if they get too violent to control? Module 5 is about how complex systems break down, how stars collapse, how life itself has nearly collapsed during periods of mass extinctions, and how human societies occasionally break down. Finally, Module 6 is about today's world, the world of the Anthropocene. How mega complex is today's world? What are the flows of energy that sustain our world? Can we manage them? Or is there a danger of breakdown? These are the questions we need to consider as we think about the complex challenge of managing the biosphere in the era of the Anthropocene.